Hello, everyone, and welcome to How Anglian Water Optimizes Flood Risk Management webinar. I'm Sean Taylor. Before I introduce our speakers, I would like to welcome and encourage you to engage with our experts today by using the Q&A box located in the right corner of your GoToWebinar interface. We will try to answer as many questions as possible during the last 10 to 15 minutes. Please note that all phone lines will be muted during this webinar. Now, I'd like to introduce our speakers. Nathan Gertz, Systems Engineer at Innovyze, Vish Naik, Hydraulic Modeling Engineer at Anglian Water, Dominique Izard, Senior Modeler at Anglian Water, and Lucy Pocock, Senior Optimization Engineer at Optimatic. Nathan Gertz is a Systems Engineer for Innovyze, helping advise utilities and consultants on how to best leverage the Innovyze product portfolio to streamline their needs for operational analytics, hydraulic modeling, and asset management. Nathan previously worked in the Innovyze implementation and support team, helping cities deploy real-time hydraulic modeling solutions and asset performance models. Lucy Pocock is a strategic support engineer for Optimatic based in the UK. She is responsible for providing Optimatic customers with on-the-ground technical support, as well as supporting new applications of Optimizer. Vish Naik has over 20 years experience as a wastewater modeler. After his graduate position at a small consultancy, Vish had an 8-year stint at Haswell Consulting Engineers and Severn Trent, then moved to Mushell, now WSP, followed by Grantmij, and has spent the last 10 years at Anglian Water working with the @One Alliance on capital delivery projects, solving flooding and growth issues, as well as serving the wider business in other areas. In recent years, Vish has taken a very keen interest in optimization and how the wastewater industry can utilize and exploit AI technologies to increase efficiencies. Dominique Izard is a senior modeler with 20 years experience within the water industry and 16 years experience in wastewater modeling. Dominique started her career at Anglian Water, and after 5 years went on to work for AECOM for 7 years, followed by 5 years at RPS, before coming back into the modeling team at Anglian Water just over 2 years ago, where she is now working with the @One Alliance teams on capital delivery projects. In her career, Dominique had the opportunity to work on many different projects and gained a wide knowledge of different modeling practices and approaches. Lucy, I will hand it off to you now.
Thanks very much, Sean. So I'm going to give a quick introduction to Optimizer before I hand over to Vish and Dom, who take us through this project in a bit more detail. So to set the scene here and for a bit of context, we want to ask ourselves, why is Optimizer valuable in network planning, in these decision-making problems? So what value does Optimizer bring? And we talk about the traditional planning process. So by that we mean, considering a traditional scope, we're going to look at hydraulic performance and cost. And these two factors are going to be what we use to drive our decision-making process. What this traditional planning process fails to address is the explosion of factors that in reality we're needing to deal with when we're making these sort of decisions in our network. So today, not only are we having to look at hydraulic performance and cost, we're needing to consider things like budget, risk, resilience, the impact of social and community impacts. So we're now dealing with a multitude of factors, and Optimizer helps us make decisions in this environment where we're having to go beyond, one or even two objectives. So we're going to take a quick poll here and just kick things off with asking, are you currently evaluating modeling options manually? So is this kind of process something that you're doing currently with your hydraulic models? Is this something you're doing manually at the moment?
Thank you, Lucy. And our responses here are frequently, occasionally, or no. We'll leave the polls open here for about 30 seconds and then share the results. Thank you. And it looks like 47% responded with frequently, Another 39% said occasionally, and then finally 15% said no.
Okay, great. Thanks, Sean. So we can see from that we're frequently and occasionally tackling these problems manually with our hydraulic model. So we're going to take a moment now to compare what that traditional process looks like compared to using Optimizer and how that changes that decision-making process. So here we're going to walk through a very conceptual flooding problem. So we can think about our flooding on our y-axis here just ranked from low to high. So we have a certain level of flooding which we have decided is acceptable, and our current system is operating above that. So that's our current problem. So in the traditional approach, I'm going to take my hydraulic model, my ICM model, for instance, and using my best engineering judgment, I'm going to test out 5 different strategies that I think will help alleviate the flooding. So these are represented by these 5 orange points on the chart here. I run ICM and I can see that 2 still have quite high flooding, and I'm going to discard those. I've got 3 solutions that I'm quite happy with in terms of flooding performance, so I'm going to take those forward to costing. So what I can see from my costing is I've got 1 solution that's cheaper than the other 2. So based on my performance and my cost, I've made my decision. I'm pretty happy with where I've got to. So comparing that to what it's like to tackle this problem using Optimizer, rather than putting in those 5 strategies manually, in Optimizer, we're going to use our engineering judgment to define what is the range of options that I'd be willing to consider, and what's the list of design criteria that I want to measure my performance against. So I'm going to give that information to Optimizer, and it's going to take that and run through hundreds of thousands of combinations of my model on the cloud. So the most important output of that are these points highlighted here in green, which is our Pareto front. So comparing to taking 1 or 3 or 5 strategies that I was happy with, I can now interrogate my flooding and see how it responds, how I can reduce it based on how much I'm willing to spend. And obviously this makes the decision-making process far more interesting. So now I can come in and see that I have the cheapest possible solution for my acceptable level of flooding, or I can choose a point that has the best value for money for our particular problem. So why Optimatics? What are our differentiators? So we have 3 key points here I want to highlight. One is the computational capacity. So the link we've built with Innovyze, which we'll touch on in a moment, taking that ICM model or your WS Pro model, taking it onto the cloud and being able to process hundreds of thousands of combinations is obviously a huge value add. The second is the algorithms. So these algorithms, they're multi-objective, we're constantly updating them, and they're specifically trained to zero in on the best strategies fast. So it's going to be very efficient at solving that optimization. The third is acting with confidence. So you can see from that last Pareto chart that I just showed, the decision-making process is now one that's very transparent. We can open that up to stakeholders, and we're able to make decisions in a very transparent and data-driven way, giving us confidence in what we're building in our network. So before I finish up here, I'm just going to touch on 5 things that you need to consider when setting up an optimization problem. And this mirrors the process that we went through with Vision DOM in this particular project, and it's applicable to all applications. So the first one, most importantly, is what's the question, or what's the problem we're trying to solve? And this is really important to frame our optimization. The second is, what is the input data that I need to consider? What hydraulic model do I need to bring in? We connect to ICM, WS Pro, so we can layer on top of that our cost data, potentially additional asset information. So what's relevant to solve our problem? The third thing is, what are the options? So this is where our engineering judgment comes in, and we need to tell Optimizer what is the possible range of options that I'd be willing to consider. The fourth, and another part that's really tied to that engineering judgment, is what is the desired performance of my system? So this is things that you would check in your hydraulic model as results. What is the performance that we want to perform to? So the fifth and final thing here is, what scenarios might be relevant? What storm scenarios do we want to solve for? Are there various growth projections that we want to optimize against? So this really takes us through that process of formulating an optimization. So I'm going to leave it there and hand over to Vish and Dom, who are going to take us through a real life project that we've recently finished in a bit more detail.
Hi everyone. Well, it's great to see everyone here. Thanks for that, Lucy. That was really interesting and a great introduction to the trial. I'm Vish Nayak, as we mentioned before. I'll be co-presenting with Dominic Izzard. We were very fortunate enough to trial the Optimatic software called Optimizer. Dom and I both work Anglian Water. We work in the capital delivery team, working on mainly growth and flooding schemes. And we trialed this software on one of the most challenging schemes that Dom happened to work on in AMP6. We generally work with the construction managers, the design engineers, and the wider Anglian Water team as and when required. So what we'll do, we'll take you through this trial and the sort of journey we took. It wasn't a straight journey. We had lots of help from Lucy herself, which was much appreciated. It was a good fun journey, and we enjoyed it. So just to start off, we want to go through the current modelling process, which I'm sure we all adhere to. And currently, and I'm sure it's the same in the US as it is in the UK, you've got a problem, be it a growth problem, or you've got growth, or you've got flooding issues, it's a risk issue, or it's a water quality issue. And along with it, you have lots of constraints. So usually the constraints are time, money, and most probably it's constructability as well. So what we do is we build our wonderful models in ICM. We let Innovyze do its magic. We send it through to the simulating machine, and hey presto, you're meant to come out with some brilliant answers. But usually, if anything like myself, you feel like you're a hamster going around a wheel, right? And you're banging your head against the wall. And you're there trying all different options, trying different pipe sizes, trying different locations. Now, the Optimizer way is very, very different, and it's actually very refreshing, and it's a nice way of working whereby you all collaborate together. So you get all the stakeholders together, be it construction managers, the design engineers, or the modeling team, and you sit down and you discuss the costing of the project, whether it's a flooding issue, a spillage issue, whether it's just risk you need to mitigate against, whether you can implement SUDs, whether you're going to use any hard engineering. This is quite a refreshing way of working, because I'm sure it's the same for everyone. Quite often when you're modeling, you're halfway through your modeling process, and you think, right, the engineer comes up to you and says, right, you can't build here, by the way, because there's a big gas main there, or there's a big oak tree and we can't cut it down. And quite often you're going back and forth, taking 3 or 4 steps forward, taking a few steps back. So that's a real refreshing way of working. The actual process with Optimizer is we use artificial intelligence, which I think our industry as a whole hasn't really exploited and utilized artificial intelligence. And I feel we're at a time now where we're kind of catching up, and it's just the right time for our industry with all the efficiencies that are demanded upon water companies. And the artificial intelligence uses a very clever algorithms. I don't understand them fully, and that's where we've got the expertise of Optimize and Optimatic's team. Where the way I look at it, in my simple mind as a modeler, is it's kind of breeds options together. So if you're trying to solve flooding and you've got 2 good options but they're not quite right, you can kind of breed them together using these clever algorithms and mathematical equations, so you get better and better results. Through this process, we're always using our engineering judgment, so you can input all that knowledge and judgment into the way the processes work. Cloud processing technology is fantastic. So you're not using your resources in the office. So once you've put this knowledge together and you've set it up and you've in effect given the problem to Optimizer, your machines and your licenses are free in your office to utilize. And the way you review results is really good. There's lots of ways you can review results, and lots of powerful tools you can use. And there's graphs and all sorts of ways, which I won't go into too much now, but we'll explain as we go through the presentation. Now, the outputs, I believe the outputs are near enough optimal. You're going to near enough get an optimal option, And what I mean by that is, hand on heart, if someone asks me, the options you've produced or put forward, are they the best options? Hand on heart, I would say they're not, but they are within the time and money constraints that we have. So we may put 3 or 4 options together, or may put maximum 10 options forward to the business. As in, using Optimizer, you can do hundreds of thousands of runs within a couple of days. So you can set everything up at 5 o'clock before you leave, or if time you leave, by the time you're coming back in the morning, you've got thousands of runs to evaluate, which therefore you'll make a cost saving because you've got a near enough optimal strategy. You get a very balanced objective because you've exhausted many options. And this trade-off curve, I think, is a very powerful tool to use. You can evaluate many options just with that one tool. I won't go into that too much right now because we'll go into it later on. We're just going to have a quick poll question, and the question is, do you limit options based on engineering judgment to make the analysis manageable?
Thank you, Vish. And our responses are frequently, occasionally, and no. We'll leave the polls open for 30 seconds and then share the results. Thank you.
Thank you.
And 60% looks like said frequently, 35% said occasionally, and then 4% said no.
Thank you. So that's very interesting, actually. So yeah, we, as mentioned earlier, we often keep our options quite minimal, just so we can manage them. So we don't always hand on heart get to the most optimal solution. At this stage now, I just want to pass it over to Dominique, who's going to explain the scheme in more detail, because it was her project that we trialed using Optimatic. Over to you, Dom.
Thanks, Vish. So as Vish has already mentioned, we have used a flooding scheme for the trial. This is a catchment in Essex. We were looking at 4 properties that had experienced flooding, both internal and external flooding, and actually both from the foul system and from the storm system. For the basis of the trial, we were just looking at the foul system, as this was a sort of more complex system that we actually needed to resolve. So obviously we went through just the normal modelling processes that Vish has just outlined at the beginning of the presentation. Next slide, please, Vish. So we added additional detail into the model. We did some surveys, we did flow surveys, asset surveys, so verified the model. It was predicting the flooding at the properties, so a really good starting point to kind of start developing solutions. I did go around in my hamster wheel for quite some time to try and develop a solution that actually worked. It was quite a difficult one to kind of get right. And that was mainly due to sort of hydraulic and also constructability issues. So the solution was conveyance in the end to actually allow flow to get downstream, further downstream to where there was capacity. Unfortunately, after we sort of developed the solution, it was sort of deemed unaffordable. Mainly due to kind of constructability. You can see there's a road highlighted on that plan. There was issues with highways, very difficult to close the road, and we actually needed to cross that road as part of the solution. So we thought that this was a kind of really good project to actually use Optimizer to see if we could come up with something slightly different, and whether we could exclude going across that road. Was there something else that we haven't perhaps thought of? So I will now hand you back to Vish, who's going to just discuss about setting up Optimizer.
Thanks, Tom. Yeah, setting up Optimizer is well, setting up the model in Optimizer is a very different way of thinking from a modeler's perspective. So at the moment, the way we model, you look at each option by itself. So if it's storage or if it's cross connection, online storage, offline storage, whatever it may be. Now, as I mentioned earlier, we have to collaborate up front, and the reason for that is we have to look at the whole catchment and decide what options you'd like Optimizer to analyze. So in this situation here, what we did, we identified that there could be storage in this location down here at the south of the catchment. There was potential a cross connection there, and we thought we could lay a new pipe there. So it's quite a nice, refreshing way of working in that you get the pool of stakeholders together up front before you start the project. So it irons out any potential surprises as you're modelling through, and it's nice that you get everyone's buy-in up front, and everyone knows what they're going to expect at the end. Now, the modelers out there may be thinking, if you're going to model the pipes in and let ICM run the model, how do you sort of turn pipes on and off? So the way we got around that was we put weirs at either end of new pipes, and we either set the weir levels at ground level or just above ground level, and therefore the pipe cannot be utilised by flow, and therefore there's no pipe there, or the weirs can be set down to invert level, and in that case, obviously, the pipes can be utilised. So we have to set the model up in this way. Once this is all set up, then we send the model up. Well, we upload it all into Optimizer, and then from Optimizer it then goes obviously into the cloud. Now, the planning criteria, so setting the boundaries in Optimizer was quite interesting. Now, Dom's going to go into this in a lot more detail, so I'm just going to touch on these for now. But the flooding penalties is a very interesting one. So the way we sort of tell Optimizer if it's doing a good job or not so good job is by penalties. So if the penalties are high, that means a flooding, or that means we're very far away from our desired solution. If the penalties are low, that means we're homing in on a good solution. So the first one is obviously the flooding penalties at the local flooding location, so at the flooding location. There's surcharge penalties, so we don't want to surcharge the system too much. Flow to treatments are an interesting one. I'm not sure about it in the USA, but in the UK, the treatment managers and the business is very concerned about how much flow we're sending to treatment and if the treatment works can cope. So Optimize and the software can actually monitor the flow to treatment. So when you've got your desired solution, you know how much more or less flow is going to treatment. Pipe costs and storage costs, that's quite self-explanatory. If it's a good option, the costs are low. If it's not so good, the costs are extortionate. Flooding penalties catchment, again, Dom will elaborate on this further as we go through the presentation, but that's there just so we know that, or just to keep an eye on the fact we're not pushing the local flooding elsewhere into the catchment. I'll now pass it back to Dom, who will go into a bit more detail on the decisions.
Thanks, Vish. So we have to obviously tell the software what it can and can't do. We're not just going to give it a free rein as to sort of say, go off and kind of do whatever you want. This is a screenshot of the number of decisions that you can think about and look at as part of your project. For our trial, we kind of only looked at a couple of these. I think it would have been quite a feat to try and incorporate any more than that. So just kind of that, this is just a list. We're sort of going to concentrate mainly on sort of conduit shape. Next slide, please, Vish. Thank you. The big thing for us was kind of looking at all the different pipes within the catchment. Now, obviously, we have a long list of pipe sizes or possible pipe sizes, sort of for us, ranging from as little as a 150 millimeter up to sort of a 1050, so quite large pipes. So we decided we would group these in the end, just to kind of make things slightly easier, because obviously there was quite a wide range of pipe sizes within this catchment. So if you've already got a pipe size where you're sort of sitting at kind of, maybe a 450, then you don't really want to sort of allow the software to kind of like have a choice of kind of thinking about whether you're going to go below 150 or below 450 rather. So you might sort of say, well, actually, we'll just kind of like put that group of pipes into sort of the pipe size large there that you can see in the middle of that table. Next, please, Vish, thank you. So in the very early setup that we had for our project, it was very much a very steep learning curve for us. So you can see there on the left-hand side, we've got categories. So where is the sewer? So is it in a road? Is it in a field? Is it brand new? Which obviously has a different cost associated with that. And then you can see on the far left-hand side, there's just a list of numbers. So that's the number of pipes in the decisions. So you can see there that there's well over 400 in there, which is a large number of pipes to kind of consider for Optimizer to consider, which is possible. But actually, once we kind of went through this kind of once we decided actually we needed to sort of hone in a little bit more to kind of give us a little bit more definition of what we kind of wanted. So in the final setup that we actually kind of went with, we had a lot more categories, and this kind of allowed us to kind of highlight areas where we knew that there was restrictions. So obviously there's the highway that I mentioned earlier in the presentation. There was also some sewers via railway, again, in terms of constructability, not fantastic. And then obviously you can see there on the far left-hand side, the numbers are much reduced. So now we're sort of over 100 pipes instead of sort of over 400. So actually kind of like really kind of honed in on our kind of area of interest. So next, please, Vish, thank you. So this next slide is kind of just a screenshot from the software itself, and it's just gives you an example as to actually how easy it is to kind of sort of set up your decisions. The sort of table at the bottom, it's just a case of actually creating your groups, which you can easily do as selection lists in ICM and kind of then bring them into Optimizer. And then it's a case of kind of, you've obviously got your cost tables, which you can add into Optimizer. And then it's just a case of actually looking at actually what you want to do in each of those areas. So it's a tick boxes to kind of, you know, do you want to upsize, downsize, leave it alone, don't look at it. And obviously then assign a shape table associated with that. So what kind of pipe sizes are you going to be looking at for those particular pipes? So once you kind of got all that set up, which was great, we sort of then moved into thinking about the penalties. Now, certainly for us, for Vish and I, we sort of never really thought in this kind of way before. So it was kind of interesting to kind of get our heads around. And I think once we kind of had a chat to Lucy and things, and we kind of like talked it through, we kind of got our heads around it. So it's sort of a very easy kind of penalty function. It's sort of exceedance times a multiplier. We decided for this project, we'd sort of break this down into local flooding. So actually on the property itself, outside the property, we basically obviously want zero flooding for the solution to kind of be, for the solution to work essentially. So we applied a very high multiplier here. But then what you also don't want to do is actually then just send the problem elsewhere. So send the problem further into the catchment. So basically you move the flooding from one location into another location. So again, we had sort of catchment-wide flooding as well, catchment-wide penalties. So the penalty multiplier was slightly lower, but it still meant that we could actually just keep an eye on what was happening in the rest of the catchment, which was kind of really useful. Next slide, please, Vish. So now we're going to go to a poll question. How many scenarios do you usually create for comparison?
Great, thank you, Dom. And our responses are 1 to 2, 2 to 5, 5 to 10, and finally 10 plus. Leave the polls open for 30 seconds and then share the results. Thank you. Great. And 71% responded with 2 to 5, 17% said 5 to 10. Thank you.
Thank you.
Thanks,
Well,
Sean.
that's probably what.
Go ahead, Bish.
Thanks, Sean. Yeah, thanks. Thanks, Dom. That poll's quite interesting, actually. So 2 to 5 is probably a standard. That's probably roughly what we do at Anglian Water, near enough. Every now and then it's a bit more, maybe. Right, just taking you over to once you've sent the Optimizer package into the cloud and it's run its algorithms and it's done its stuff, you get lots of results. And this is one of the results that we got in graph form, and it's far off the 2 to 5 that we kind of got the 70% from. It's more like hundreds of thousands, and dare I say maybe into the millions possibly. But each dot you can see there on the graph is actually a potential option. Now, the y-axis is a flooding, so that flooding is made up of catchment flooding and local flooding. However, as Dom mentioned earlier, there's more weight put on local flooding, so that's what we want to solve. And the bottom is cost in terms of risk. So you'd think the most optimal would be in the most bottom left corner. However, what we did was we evaluated just the green dots you can see there, and the reason for that I'll explain in the next slide. But just come back to looking at this. A lot of modelers will be thinking, wow, it's hard enough to kind of evaluate, 5 options or 10 options. How do you evaluate this? But it really is a very simple process. Dom and I, we thought, wow, this is going to be very daunting. But there's a very simple process in Excel. You can filter down whether you want it for cost or for performance, and you can filter it according to the flooding, and then you can pinpoint your options you'd like to bring out from Optimizer and download into out from the cloud into Optimizer, then from Optimizer into ICM, and it literally is a click of a finger. And when we saw the results, Dom and I thought, wow, now it's going to be a struggle, but it really wasn't. It was a very simple process. So I just want to explain how the software sort of went about getting to the solution and why the most optimal isn't where we thought it would be at the knee of the curve. So having seen so we evaluated most of the results where it's highlighted there in the red circle, and the reason being is, as you can see here, on the left y-axis is local flooding and the y-axis on the right is catchment flooding. So the blue dots represent the local flooding. You can see as Optimizer was running the algorithms and it was running its processes, the flooding was coming down. However, you can see that all it was doing was pushing the flooding elsewhere. Now, to us, this was quite nice to see, because in effect, this is what happens to most modelers. You're solving it in a local area and it just pushes it elsewhere. So what the program done, obviously, got to a certain point. So hang on a minute, the penalties are increasing too much, so we need to push it further down, and that's why we looked at options in just not at the knee of the curve, but just a bit further along the graph. So once we allocated the options that we preferred, we sort of narrowed it down to, about 10. But then we brought into this for this presentation, we're just going to discuss a few here that we've got in this table. So I'll now pass it back to Dom, who will explain this table in more detail. Over to you, Dom.
Thanks, Vish. So as Vish said, the Pareto curve, I have to say, just personally, was just like, wow, like, where are we going to start? Kind of like looking at all these kind of different options. I don't think I've ever seen so many different options or possibilities. But it was really interesting, like having the experience and kind of like figuring out how best to kind of look at the results, and as Vish said, very easy to kind of like do some jiggery pokery in Excel and kind of filter and kind of really look at sort of narrow down your search of actually what kind of options you want to look at. So this table is, so the left-hand side is the flooding criteria, which we set up and discussed earlier. The input model is essentially our baseline. The manual plan is the solution that I developed in the traditional way. And then the 3 columns to the right are kind of the options that I'm just going to discuss very briefly. I just wanted to highlight the one in the middle, which is a storage solution. So for us in this trial, in this catchment, we quickly, very, very quickly discounted storage as an option. It clearly wasn't going to be, it wasn't going to work in this catchment. And the reason you can really easily tell is that there was a 121% increase in cost. So immediately, if you went to the sort of design engineers and said, oh, here we go, we got a storage option, they just sort of say, no, that's not happening. So very easily and very quickly, we could discount quite a few options, quite a few of the results to say, actually, the storage works, but actually it's just going to be way too expensive. So the one that we kind of took from Optimizer was this cheapest, no local flooding, no catchment flooding. And you're probably thinking, well, actually, that hasn't resolved the flooding because there's a number there in the penalties for local flooding. But the multiplier that we set up was so huge that this actually equates to very, very small, less than 0.02 meters cubed of flooding. So very, very small, very, very small amounts. And obviously you can see there that there's a reduction in the cost in comparison to what I originally developed. So what we decided to do is kind of, obviously, as Vish has mentioned, very easy to take this into ICM. It just creates a new scenario and it brings over some flags so you can quickly filter in your grids to actually find what the solution is, where the solution is, what kind of pipes have been changed. And once we looked at the results, we thought, well, hang on a second, it's done a few things that we weren't really expecting. Why is it kind of upsized some of the pipes that it had? So we decided to make our own modifications. So we kind of took the original kind of solution from Optimizer and then made some modifications. So we moved some of the upsizing, and actually, does that still work? And the answer was yes, it does still work. But actually, it gave us a further reduction in costs. So at that point, we were kind of working between ICM and Optimizer, so kind of doing some changes in Optimizer to kind of get these numbers that are in the table here, but also running stuff in ICM as well in parallel, so we could actually understand whether the option would still work. Next, please, Vish, thank you. So this is basically, this is our preferred solution. So I just wanted to kind of show you what it actually looks like in Optimizer as well. So obviously we know what it looks like in ICM. So in Optimizer, again, it's quite visually very, very easy to see what's different in comparison to kind of what it was before. So this is just a kind of legend that you can create. It shows the pipes that have been changed, actually upsized, and the colours are indicating the sort of the pipe size itself, so sort of different range of pipe sizes. So I will now hand you back to Vish.
Thank you, Dom. I think we're going to have another poll question. So, do you account for social, environmental, and/or carbon impacts as part of the optioning process?
Great. Thank you, Vish. And our responses are social, environmental, carbon footprint, a combination of the above, or none of the above. We'll leave the responses open for 30 seconds and then share the results. Thank you.
Well, we all know what the right answer should be.
And 69% said a combination of the above, and 18% said environmental. Thank you.
Thank you very much. That's interesting. Yes. Yeah. I just when I saw this poll question earlier, I was thinking, well, there's only a certain amount that the human brain can actually process. As in, you use artificial intelligence and clever algorithms, you can incorporate so much more. But that's interesting that we try our best to use a combination of all of the above. Right. Just in finishing off now, if I can get to the next slide. one thing that I thought when I saw this, I thought, this is great. I said, Don, we can just come in, click a finger, and we can go off to the pub. But it's not it's not as simple as that. You know, we still need our modelling expertise. You still need that hydraulic knowledge and all the experience. And then there is a computer, garbage in, garbage out. But what I found really, really useful was the process that we have to follow. So pooling that knowledge from all the stakeholders, from all the business, is something that sometimes we do, sometimes we don't. But this process forces you to go down that route, so you can really discuss up front which options you want to consider, which you don't. You know, the costs, and you know, you can then rediscuss, is the option fit for purpose, and you can have everyone's engineering judgment put into the process right from the offset of the project, which we should be doing. But I think just because of the nature of the way we work, it doesn't always happen, especially for modelers, because you, as I said earlier, you go through this process and then questions come out from that, and then you have to go back to engineers or go back to the construction managers, and you're kind of fishing for data as you go through the process. Now, where do we see the future? Well, I'll tell you what, it definitely takes away all the repetitive tasks. There's all those mundane tasks that we hate to do, and it's great just to let the artificial intelligence, the algorithms do all the sort of donkey work as such. And it's nice just to be able to package it all up, send it off to the cloud, and therefore you're not utilizing your resources in-house, which means from a business perspective, you get your morphing modelers, utilizing your modelers on more the detailed hydraulic engineering side of things, as opposed to the repetitive tasks. Again, exploiting artificial intelligence, I mentioned it earlier. I don't think our industry really does compared to other faculties of engineering. I think we kind of were lagging behind, although I do feel now, one, the industry is ripe and ready for it, and secondly, I think everyone's more open ears, and we can definitely exploit artificial intelligence because now we have, the software available, which obviously saves time, and for businesses, especially with all the efficiencies imposed by Ofwat, it saves time and money. And the evolution of options is an interesting one. The fact that the algorithms, kind of the way I look at it, breed the best options together to create even better options, I think is fantastic. Now this trade-off curve, I just want to end on that. I just think it's one of the most powerful tools we've got, because quite often you've got your singing and dancing solution, you go out on site, and for whatever reason, you just cannot build. There might be a gas main or whatever it may be. There's the numerous reasons, and quite often for the modelers, it's back to the drawing board. There's a lot of pressure. You've closed the roads off. You've got men out on site that are waiting to do something. With all these options in place, it's click of a finger. You can see the next best option, download it, it's into ICM, run it, make sure it works, and off they go. And within 24 hours, you could have the next best solution in place. So on that note, I just want to say thanks to everyone for listening, and I'll hand you back to I think it's Nathan.
All right, thank you, Vish and Dominic. I'm going to start sharing my screen, and I think we should be up. And so, yeah, that was a really interesting story, and it's kind of an optimistic look at the future, that we don't need to keep spinning that hamster wheel and being the donkeys of the process. I think you mentioned. So yeah, I just wanted to follow up from an Innovyze point of view. You saw that InfoWorks ICM was used in this project, and I just wanted to follow up as a perspective of why InfoWorks ICM provides a really good foundation for this optimization work. There's a number of different modeling software out there. Innovyze has several in this space, but we've chosen InfoWorks ICM as well as InfoWorks WS to kind of be this integrated partner with Optimatics because of the reasons I'm going to mention right coming up. So why use ICM? So I'm going to step through a few of these. So it's great for configuring the model, solving the simulations, and then reviewing your final solution before you're putting in that investment into the ground. So stepping through these and starting off with configuring, InfoWorks ICM is pretty widely regarded in the industry as an excellent solution for being able to represent the current system, the current problems, as well as the solutions. So Anglian Water had to be able to accurately represent their current flooding problem and to be able to understand the exact physics going into it so we can test out solutions. And we also need to be able to then simulate those actual solutions, whether it be with green infrastructure or other solutions. So ICM is just a very versatile product for being able to represent those exact physics in a really realistic manner. Similarly, there are tools that you can help use ICM if you need to adapt your model for speed. It's really easy to leverage multiple different resolutions if you wanted to simplify your models, and you can kind of expedite the iterations of simulations. And also, you saw that sometimes if we're looking at different pipelines, what they did in this project was they set up multiple different pipes, and then they close them or open them using weirs. So with ICM, I find that when I'm working in it, it's a really good platform for being able to manage large systems or many different iterations. So rather than manually clicking, it has a database that is already geared for being able to apply widespread changes based on logic. So the database understands how the connectivity is applied. You can understand which pipes are connected to which nodes and which subcatchments, which gives you a framework for being able to write SQL queries, for example, where you can write just a little quick bit of code, and you can then apply widespread changes to make, create objects, edit objects, delete objects throughout your network without needing to manually point and click a bunch of times. And you can also then take it the next step to Ruby scripting if you wanted. I'm not a Ruby scripter, but I was able to write a simple query that was able to generate many different scenarios for model sensitivity studies. And then finally, you can also then leverage nearly unlimited scenarios. So it just creates a platform where you can test out and QA/QC many different arrangements and possible solutions in your model without needing to manually point and click. So the next step is solving the model. So ICM is kind of regarded as one of the faster engines, one of the fastest engines in the field. And one of the reasons is that it uses a fully implicit numerical scheme. So that means generally larger time steps, and you also get reliable results in less iterations. Similarly, it can definitely do parallel processing, so it can use the full CPU, queue up simulations in parallel or in series. We can use GPU acceleration if you're doing any 2D simulations, and it's also integrated so you can leverage multiple computing resources. So you can farm out simulation tasks among different computers. And so to illustrate that, you could have an engineer working on their laptop. They can be connected to other servers within your network. And then other engineers can also be connected to that pool of resources, and you can just continue scaling horizontally. And so this same model has been applied in the cloud with Optimatics. So they have many different engines all integrate, all set out horizontally for being able to simulate these hundreds of thousands of simulations in a relatively short period of time. So then finally, reviewing the model, we saw that you can obviously review the many different options within the optimizer solution. But before you then make that significant investment, we saw how Anglian Water then brought the model back into ICM. So they brought their optimal solutions into ICM. You can reintegrate it with the full detailed model. And then with that, you can then review all of the different processes and how they're interactive. So ICM gives just a good visualization for being able to look at dynamic maps, profiles, graphs, 3D views, and so that you can and you can also track the individual changes made by Optimizer. So every little change that Optimizer recommends, you can then see what it was versus what was the previous value. So it's pretty transparent, and you can use this visualization for stakeholders. So this just helps you notice any unanticipated consequences from using a genetic algorithm to create optimal solutions. So in this case, they were able to easily spot downstream or flooding being pushed to other spots in the catchment. They were able to catch that within the optimizer, but depending on whether or not you caught that, this kind of gives you that extra layer of kind of thorough review. So in summary, with ICM and Optimatics, it is a fully integrated solution. We've been working with them. We're pretty excited about it. So here we have multiple engineers on different desktops or what have you. They can be leveraging InfoWorks ICM, and these can be interconnected using ICM servers, so you can have a shared database, shared remote engine. Similarly, they can also access the Optimizer tool that can be integrated, and that could be connected to the Optimatic's cloud services. And Innovyze and Optimatics work together to develop a direct API connection, so that when you're asking for new runs from Optimizer, it can then directly pull from your latest model from your ICM data server, run those many iterations on their cloud resources, and you can easily pull them back into ICM. So at the end of the day, what you get is optimal designs with confidence. Is kind of the final kind of takeaway. And so last little comment is that this project was using ICM. It's for a sewer storm system, but we also have water modeling integration with InfoWorks WS Pro. So with that, I'm going to wrap it up with a final polling question, and that is, would you like further information? So that question is going to pop up.
Great, thank you, Nathan. And our responses are yes, I'd like to know more about optimization. Yes, I'd like to know more about ICM and flood modeling. Yes, I'd like to know more about ICM and optimization. And finally, no, thank you. We'll leave the polls open here for 30 seconds, and then we will jump into the Q&A session of the webinar. Thank you.
All right, thank you. So we are going to jump over to some question and answer session. Let me just make sure. Yep. So I'm back sharing. So if you haven't already, go ahead and find your question panel in the GoToWebinar panel, and you can enter in any questions, and we're going to start to share some questions. So one of the questions I noticed is, did you consider green infrastructure as one of your decision tools in the Optimizer? So Vish and Dom, did you guys want to kind of answer how you handled green infrastructure versus our traditional solutions?
Right, we didn't actually. Right, okay. In this scenario, we didn't. However, you can very easily do that. Basically, you can set up Optimizer to decrease or increase any hard area and make it a green area. Then you'd need to do some detailed design of how you'd actually implement SUDS. So I guess that's what the question's aiming at, is can we look at SUDS? So I know Lucy may be able to jump in here, but I know Optimatics are working on SUDS solutions, should we say?
Yeah, for sure. So it's definitely something we can consider. You know, Dom, one of the screenshots there had a list of the possible decisions we can use. We're also able to add to those pretty easily. So we're constantly sort of adding new options. So we do have various decisions which allow you, as Vish said, to sort of, either on its own we're just looking at green infrastructure, or, in parallel with maybe you want a combination of green infrastructure with, maybe some pipe and storage solutions. So we're definitely able to add that in as a decision, either on its own or in parallel.
Great. Yeah, that was a good question. Here's another quick question that sounds interesting. So the question is, do we know how much time it saves, or too early to say? You guys want to comment on that?
It's a really good question. Dom, did you want to jump in?
I was just going to say, I'll let you jump in as well, Lucy, I think, after I've finished babbling. I think for us, we can definitely see where it could save time. I think for us, it's one of those things when you're kind of learning something brand new. It was this very steep learning curve. It did take slightly longer than obviously what you would it would normally. But now we fully understand the process, and actually kind of getting things set up and we could see in the future kind of using that again would, you know, be much quicker. And obviously, as Vish was saying, once you kind of have that upfront collaboration with all the engineers and stuff, you kind of know what direction you're kind of going in. You can really kind of start to plow ahead and kind of get everything set up. So, Lucy, you want to add to that?
No, great point. Yeah, I was just going to add sort of, yeah, this was a pilot project for sure. So, yeah, lots of great learning from these guys. But as you sort of mentioned, Dom, you know, doing it again would probably be more efficient. And I think just in general in projects we see, does it save time? You know, it depends on the application you're looking at. Sometimes you'll spend the same amount of time as you would say manually, but you've taken the investigation really so much further than you would have on your own. So the quality of the results is greatly improved. And if you're doing a problem that's, you know, maybe a bit repetitive or similar, and you're getting into those sort of consistent analysis, then there's definitely, you know, economies where you can reuse parts of formulations from one to another.
Yeah, can I just add to that? I think where the cost saving is, or the time saving, it's not so much time, but time is money. So I believe where you save a lot of time is you get a more of an optimal solution. So for the business, you actually get a lot more for your money as such. And quite often or not, where the time gets zapped up is, can we try a 450 pipe in this section here because we can't fit a 600 in, or an 800 or whatever it is. And with this, there's a good chance you can just go into Optimizer and there'll be an option with that length of pipe at the desired width. And I think that's where you make a lot of savings on time.
Yeah, good question. I see a couple questions regarding carbon targeting. There's a longer question, and I'm gonna use the shorter question. So, in addition to the cost, can carbon calculator be added as well, kind of considering the carbon footprint of a project?
Yeah, it's a really good question, and it's definitely becoming one that's more and more relevant, you know, as carbon becomes, you know, a more of a priority. So it's definitely something we can consider. I sort of mentioned before, we're able to add functionality and expand, you know, what we currently have in terms of decisions and design criteria. So we're able to add those in. We've set up the platform to be quite dynamic, where if we have a way to calculate carbon based on which options are selected, then we're able to configure that just in a scripting language, and we can bring that in. It's just a zip import to expand the functionality to alongside all that functionality that we have already. We can also add that sort of carbon quantification to enable Optimizer to add that as an objective. And so that could be incorporated, you know, with performance. It could be a third objective. So you can see, you know, cost, hydraulic performance, and then on the third axis, you'd have your carbon impact. So again, that's just sort of expanding your multi-objective optimization into another direction.
Yeah, we're getting a lot of good questions on kind of the cost functions within Optimizer. Here's just another one. Can Optimizer work out catchment-wide solutions for multiple problems with careful definition of the parameters? So like this was focusing on kind of one problem, but what if you're balancing out a few different interacting?
Yeah, it's a good question. It's one that's going to be perhaps difficult to give a very clear answer to, but Optimizer is definitely looking at, you know, it's catchment-wide planning. So, you know, we're not just looking at the one pipe that's flooding, or, you know, the certain elements we're considering for upsizing. We're able to apply those decisions and those design criteria across our whole hydraulic model. So as you say, it's a really good clarification, you know, with careful calibration of the parameters, you know, we're able to add in different options that may not be directly related. In Optimizer's mind, it doesn't actually mind if this pipe's not connected to that storage tank. It's if we define those options in a logical way, then we're going to be able to consider them with an Optimizer. So I will say on that, you know, there is a limit. We don't just put in a network and allow every pipe to be changed, every option for storage to be put at every location, and green infrastructure everywhere, and just tell Optimizer to tell us what is the best setup of our network to solve everything. we do need to target, the question somewhat, but we are able to consider sort of different options. So a bit of an answer in the middle there, if that makes sense.
Yeah. There's one real quick question I'm going to answer real quick. What hydrology and hydraulics routines does the software use? So with ICM, it's going to use any, Optimizer can use anything within your ICM model, so any kind of hydrology routines and full hydraulics, but not all of them are necessarily required for optimization. So you might not want to use a detailed 2D modeling if you don't need to, because it's going to take a little bit more time for simulations. So that was another question, is can you kind of summarize 2D flooding, where and how bad it's going to occur, so you could do things like stored flooding on nodes to understand, how much flooding is happening at the nodes, but you're not actually simulating the 2D flooding, and you're just trying to keep that volume to a minimum. So I guess we're running low, but one last question. Do you think the software is practical for designing small systems? So like for small commercial sites, so like maybe, if you had Optimizer, could you, apply this to multiple, small different projects? Any thoughts, like how small can you go?
No, it's a good question, because on one hand, we can look at, these really wide strategic networks, say, and really look at a quite a large area and take into account, quite a large scale model. But then on the other hand, we can use it at a fine level. Optimizer doesn't mind. It's really just about the detail that we want the answer to. If you're balancing, more options than you could feasibly hold in your head, these small problems can very quickly, scale up into, well, where should I put the pipes and how big and what storage and what about green infrastructure? So even on small sites, you can throw more options at it when you're looking at it in Optimizer than if you could on your own. So I'd say that, we'll tell you if a model is too small. We're very happy to work with you to identify if it's not going to be valuable, but, we do see a lot of value on small networks as well.
Awesome. Well, we are running out of time, unfortunately. We did have a few more questions, so we will be going through our question list, and we can follow up if there were unanswered questions, and there will be a recording of this session. So, Sean, do you have any closing comments?
Thank you, Lucy, Vish, Dominique, and Nathan. We would like to thank everyone for attending today's session. If we did not get a chance to answer your questions today, we promise to get back to you with an answer. Thank you and have a great day, everyone.
Thanks, everyone. Bye.
Thanks.
Thank you.